Welcome back, my friends. Nice to have you here on the channel again. Today with part number 2 of our parallel extreme test. Directly here from the off-grid garage in sunny, hot Australia. Welcome back, guys. Well, in the first part we have talked a lot about the test setup environment here and what to consider when you parallel battery banks together. And now in part number 2 of the test video series here, we want to go a little bit further and use the high power charger here, the 21 amp charger, and charge this battery parallel setup. Okay, let's start this test and see if everything works out, or if we actually reach the limit of the parallel setup here and the BMS will finally turn off. Remember, we have set up both BMSs to protect our batteries here from high currents, charging and discharging as well. And I have connected the crocodile clamps to the positive bus bar and to the negative here. Everything is ready to go. We start the recording for both BMSs here, and interestingly that I can actually see a current, a charging current going into the parallel cells. This power supply is not turned on yet. There is a 0.6 amp eddy current going from the EV battery to the parallel cells at the moment, and I'm turning on the power supply right now, and let's see what happens, how much current does actually go into the parallel cells and how much power goes into the EV cells. Why is it not working? I've now set up the power supply correctly, 13.8 volt and 21 amps, and we turn it on and watch the current for the parallel cells and the EV cells. Okay, we are charging only with 3.9 amps at the moment. 1 amp is going to the parallels and 2.9 goes into the EV. Okay, I'm increasing the voltage slightly now to increase the current. 14 volts. And we can see we are charging with 2 amps into the parallel cells and 8.7 into the EV cells. It does the distribution just by itself. Okay, we're going higher. So 14 volt would mean 3.5 per cell. We're going a little higher. And now we are exceeding the 3 amps for the parallel cells, and 14.8 amps are going into the EV cells. So 15 amps to 3 amps now. This is the maximum charging current the parallel cells should get. The BMS should actually turn off, right? I just say it and now it turns off. See, the BMS is now protecting the battery cells because this is the threshold we have set. And then the BMS kicks back in, looks if the high current is still incoming. Yes, it is. So it will turn off after 10 seconds again. And we can also see the deviation is now getting larger in the parallel cells because they are charging with over 3 amps. So this is a limitation now of the parallel cells, of course. This is a very extreme test what we are doing here. Super high capacity cells, super small capacity cells. And you can see here we're charging with 4 amps into the parallel cells, which is over the specs. So I'm lowering the voltage again here, just to make sure there's not too much power going into the parallel cells. And still 3.6 amps, which is too much. So going down to 14 volts, 3.5. That's 8 amps all in total, 9 amps and 3.5 going into the parallel. BMS should turn off after 10 seconds. There it is, turns off. And then obviously all the current goes into the EV cells because they can just take it. Okay, let's turn off the power supply and see what happens now. So now we can still see the EV cells are actually providing power, 1.6 amps, to the parallel cells. We've got an eddy current of 1.6, 1.7 amps. Let's see if we can measure that here. Yep, there it is, 1.8 amps. 1.8 amps. Of course, there's nothing else connected, nothing else turned on. It's the noisy fan. So 1.8 amps coming from here, going through the bus bar into the Palo cells. And interesting here again that our battery cells have different voltages. The Palos are at 3.4 and the EV cells are at 3.42. So we've got a slightly higher voltage in the EV cells than in the Palos. That's why we have an equalization current from this bank to this bank. I'm not expecting that this actually happens if you use the same capacity cells and parallel them. Again, this is the extreme of the test. Interesting is that we still have an eddy current of 860 milliamps going from the EV into the Palos. So this short amount of charging we just had here for the test has obviously triggered something. And the EV cells are holding the voltage far better than the Palos. And these are obviously not as charged as these ones are. Quite interesting. Well, so after an hour now, we are still having an eddy current from the EV into the Palo. So obviously we have a significant different state of charge here. And once I apply power from the charger, the EVSE voltage is rising because we are already going into this steeper area of the curve, while the Palo cells stay down because the state of charge is just not there. Voltage is very similar, but state of charge is not there, and the voltage of this pack is rising faster. So current is going from this pack into the Palos. I have now connected only the Palos and charged them up to the same voltage as the EV cells. But, you know, I thought, well, it doesn't really matter because it still shows the basic of what I want to show you. So let's just continue with our discharge test here. Okay, disconnecting the charger, turn the EV cells back on. Okay, I think I've got them now. We've got 100 milliamps of eddy current from the big to the small one. That's all right. Okay, I have now connected our light bulbs here, and we are using only these two, which is, I think, 80 watts or so, 8 amps, around 8 amps they have at 12 volts. So these are the only ones we connect at the moment and want to see what's going on. At the moment, both BMSs show 0 amps, so there's no current flowing apart from our eddy current, 200 milliamps from the big to the small one still. Okay, I'll just connect the, let's see, there's no spark, no, okay. Whoa, that is bright straight away. And now we can see the big battery is delivering 7.8 amps, while the small Palo battery is only delivering 0.5 amps. See, we are seeing a very similar behavior now while discharging the battery as well. The main power is coming from the EV cells and only a small amount is coming from the Palo cells now. Okay, let's see here, 8.1 amps and 0.3 amps coming from the Palos only, 0.3 amps. Okay, let's turn this off again. And let me connect another row of light bulbs here so we have a larger load. Okay, so this will be significant more load now. I'm not sure if using the crocodile clamps here, I'm not sure how long they will actually stay here before the insulation starts melting. So we can do this only for a short amount of time now. This will be a lot of current now. Let's see. Oh yeah, that's a sparky here. And bam, oh yeah, that's bright. Okay, 3 amps from the Palo and 20 amps from the EV cells. Here, let's measure again. Yeah, 23. Oh, something is hot here. And, oh, there's magic smoke. Quick, 2.4 amps. There's the insulation going. And we have magic smoke, and this is already pretty hot. Whew. Okay, so, but as you have seen, the majority of the work is being done by the large capacity cells, by the EV pack, not by the Palo. So you can actually parallel battery banks with different capacity without any problems. Okay, so, and now I want to actually show you why this is as we have just seen it. And we use our internal resistance meter. Find a spot where it's not reflecting. Of course not. There's always something reflecting. Hang on. Camera like this. Yeah, that's all right. Perfect. Okay, I'll turn off both circuit breakers so the battery banks are isolated. And I'm measuring just the internal resistance of each of the battery banks, including BMS, including cabling, including all the connections, including everything from the circuit breaker to the battery. And I do the same for the EV as well. Okay, so negative going over here, positive over there. And we have here with the Palo cells an internal resistance of 58.4 milliohms. 58.4. So, and now we are measuring the EV battery bank. And we have 11.66 milliohm here. So, and here is what we basically have. We have two battery banks, the EVE battery and the Palo, in parallel. Yeah. So positive is connected to positive. This is our bus bar here. And the negative and negative are connected via this bus bar. The Palos have 58.4 milliohms. The EV has only 11.6 milliohms. So far less resistance here. And this obviously makes a big difference while charging. If you connect the power supply here, positive and negative, what the current actually sees is this lower resistance path and this higher resistance path. So most of the current will go through the EV cells to the negative port, and only a small current goes through the higher resistance path here to the Palo cells. And the same as while discharging. Because of the far lower internal resistance, the EV cells will give more power than the Palo cells. And this is exactly what we have just seen when connecting the light bulbs. Almost all the current came from the EV cells and only a very small amount came from the Palo cells. And again, this is why you can parallel these battery banks even they have different capacities. Well, nobody would actually build such a battery here, of course. This is just for testing and demonstration purposes. But if you say you want a 280 ampere hour battery pack parallel with a 350 ampere hour battery pack, there's no problem at all. These are almost the same capacities anyway, and there's very little eddy current flowing between these two battery banks then. Once they are equalized, it will be just fine. Okay, so the next test would be, I would like to fully charge these battery banks to 3.6 volts now and want to see what is going on. We will take our power supply now, change it to 3.6 volts and then connect it and see what is happening. Because I believe the EV cells are higher charged already. They have a higher state of charge. They will reach the 3.6 volt very quickly, while these ones will take longer. And I'm keen to see when this voltage is rising, if there is actually current going from the battery bank into the smaller Palo battery bank as well, and potentially overcharge this one here. Remember, we have set a 3 amp threshold in the BMS, so if we go more than 3 amps, it will turn off the charging cycle then. Okay, without further ado, let's start the test. I've written all the numbers down. 3.6 is 14.4 volts. Okay, we set 14.4 here. We go full power, maximum amps. Okay, so let's turn on our circuit breakers here first and parallel the battery banks. Let's see if we have, 3.5. And the BMS turns off of the Palos. Did you see that? That's why you should have a BMS. And now we are under 3, so the BMS should actually stay on. But look at this voltage difference. What do we have? 3.44 in the EV and 3.42 So it's actually not that much, but still 1.6 amps. Alright, this only gets worse when I connect now the charger actually. Okay, let's do it. So I think the EV battery bank voltage is rising faster than the voltage in the Parallel cells. 3.45 we have in the EV. Oh, maybe I'm wrong. The current is actually tapering off at the Parallels. So they seem to catch up now after the initial shock. Okay, we are charging with 5 amps all in total. 4.2 in the EV and 0.7, 0.8 into the Parallels. We can see the deviation is rising in both battery banks. That means we are slowly approaching the steeper part of the curves. More deviation, and it's rising quite fast actually now. 3.5, cell number 3 there. And the same for the Parallels, cell number 4, 3.5 we have reached. And now we can see the current is tapering off at the power supply. Under 5 amps now. And there's nothing, there's 0 amps going into the Parallels. Look at this. Everything is going into the EV. I haven't turned on the balancer for the Parallels with the Xiaoxiang app here. I'm not sure where the settings is, if it's still at 3.6 or so from the last tests, but it doesn't matter. So we should actually see 3.6 volts of all the cells at some stage. But I think this is just the voltage drop we have here on these thin cables coming from the power supply to the bus bars now. Yeah, we've got only 14 volts here, not 14.4. So we've got a massive voltage drop from the bus bars here to the actual power supply. That is disgusting. I'm not sure why we should use this power supply here. Why am I using the small one? Okay, this is not the outcome I was expecting actually. I thought because we've got a higher state of charge in here, this one will rise faster and therefore there will be an equalization current going from this battery bank into the smaller one. But it's not the case. This one has catched up already and voltage is rising slowly. We are at 3.56 volts. We're still charging with 2.2 amps, but well, this effect did not occur. Okay, I'm a bit surprised. And they will charge up to 3.6 now until the current basically goes to 0 and the battery banks are... See, as you can see, it is not a big deal to parallel these battery banks, as many of you have stated under the first part of this video here. And thank you so much for all your 160, 180 comments. Insane! Thank you so much. Well, I guess so far we have explored everything with these two battery banks here. What I found quite interesting is that some of you guys have actually shared their experience with having different chemistries in parallel. I thought I've read 2 or 3 comments that people have actually combined lithium iron phosphate, lithium ion, and GL batteries, so lead acid batteries, all in parallel, all in one system, all connected, and this seems to work. So I'm quite surprised that this actually works. Because, for example, if we have a quick look here at these 2 charging curves for lithium iron phosphate batteries and lithium iron batteries, they have a different charging curve. So in this part of the curve, when we start charging, the lithium iron phosphate battery wants to charge fast, so the voltage rises actually much faster than from the lithium iron battery. But it cannot rise because it would then charge with an equalization current the lithium ion battery. So I think in this part of the curve it follows the lithium ion curve, but at this point of time then it changes to the lithium iron phosphate curve until the voltage actually rises at this point here. And then the lithium iron gets charged as well once this voltage is rising here. So it will be a very, very strange and interesting curve. That would be actually something I would like to test here with a 24 volt lithium iron phosphate battery and a 24 volt lithium ion battery. And then we could use the CKE Tech tester and draw the curve and see what's actually happening and measuring the amps going into one battery bank or the other one. Well, we've got this set up now here. I'm more than happy to use some of my 18650 cells, and we put them in a, should we put them in a 3S or in a 4S configuration then? That's why people build 24 volt batteries, because there's a much better match of the voltages between lithium iron phosphate and lithium ion. I don't think we can do this test with the 12 volt battery here. Well, I need to order 24 volt BMSs then. Can I use the QUCZ BMS I have and the JK BMS? I certainly can use the JK BMS. Okay, I'll figure something out. And here we have a quick look at our battery cells here. We can see we are at 3.6 volts. And here we are at 3.6 volts as well. So all the cells are the same basically. We've got 8 millivolt deviation and 6 millivolt deviation. The balancer has kicked in here, and this one gets balanced anyway with our active balancer I had connected here. So both batteries are now at 99.9% state of charge. The Palo has caught up to the EV battery bank, and everything seems to work just fine. We're still charging with 0.4 of an amp. Absorption current now mainly going into the EV battery bank. Okay guys, I think that's it for tonight for this test with our two very different battery banks here in parallel. And this is actually something I wanted to do for a long time. I was always wondering what is happening if we actually destroy the smaller battery bank. And we have seen we actually do in certain conditions. The current into the Palo exceeded sometimes 6 or 7 amps I've seen here. So my expectation of this whole setup was actually it will work, but we need to pay far more attention not to overcharge the Palo cells. The overall outcome now of this test, it was much smoother than I was expecting it actually, I must say. Okay guys, leave your comments down below if you have set up lithium iron phosphate in parallel with lithium iron, in parallel with lead acid batteries. How do you control the current then going into lead acid? Does it do this automatically because the internal resistance is just higher in lead acid? I would love to hear your comments about this, and also if you would like me to set up a 24 volt system here, 2 of them, lithium iron phosphate and lithium iron, and we do the tester with the CKE test and do a proper curve, charge and discharge curve. That'll be an interesting test, I think. Okay guys, until then, stay charged, stay safe, and thank you again for watching. See you then. Bye bye.